Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. In today's paper, we're going to dive into the world of image segmentation from X-ray computed tomography, specifically for fatigue-initiating pores. This work comes to us from Carnegie Mellon University, lead author Justin P. Miner, and corresponding author Sneha, Prabha, Narra. Okay, so X-ray CT, this is a fantastic technique. It is useful for investigating in a non-destructive way the internal pores that could be causing the flaws when a material fails due to fatigue. It's become sort of the gold standard. But it's inconsistent in how you go about segmenting what's material and what's a pore. People have used a lot of different tools, so dice coefficient, intersection over union, these are typically widely used. And there's lots of different thresholding techniques out there. Right, they've got global thresholding, adaptive, hysteresis, even UNETs, right? In this specific work, they're going to be using the AM Bench 2025 data set, which came from NIST. It's a fantastic data set of images for these materials, and they're going to explore what's the best segmentation tool to use, and can we merge our domain knowledge to make it work even better? Let's dive into it. So here's a good example of a X-ray tomography reconstructed slice, right? And if you look at this thing, you might not notice it, but if you zoom in, there's these little specks, right? Those little specks are pores. And if you did just a classifier, segmentation model, and you asked me to tell me, well, where's the metal? It might identify these things in blue. But the problem is some of these pores are completely inside and some are on the surface. And this is where it gets tricky, is the segmentation model's job is to identify the part from, say, the background. And if this is breaking the surface, that background pore might get deemed part of the background. But we know as material scientists, that's not just background. That's a very important pore. Obviously, when pores exist at the surface of material, they have twice the negative impact, right? Due to the way that the loading is present at the surface. So what the authors do here is a clever step. They do this intended part geometry smoothing step, which basically allows us to realize that, oh, the part was intended to complete that circle there. So that's not just air or background. That's something else. Once you do this intended part smoothing, then they can do the pore classification or segmentation. And now you've identified that there's a pore here and a separate pore here, which was really near where the surface should have been of the intended part geometry. So this is a better way to do the segmentation. Now, at this point, if you ask it to correctly identify pore versus metal, let's take a look at the performance of the different models. So here's the confusion matrix for binary thresholding, adaptive thresholding, hysteresis thresholding, and UNET. And in these sort of confusion, what you'd like to see in these confusion tables is like when the true label is a pore, you'd like to see that the predicted label was also a pore. When the true label was metal, you'd like to see that predicted is metal. It's having no problem capture the overall performance of metal, right? Almost 100%. But the pores, it's only getting it right about 80% of the time. The other 20% of the time, depending on the model, it's thinking that it's actually a metal, so it's getting those wrong. Now, one thing that a data scientist who's not a material scientist would do is they'll say, well, the vast majority is metal. So what you need to do is give it something like a dice score, right? So intersection over union or dice coefficient will improve this, right? Telling it to focus more on the pores, even though it's a small amount of the total voxels in the image. And that does a little bit better, but still, take a look in table 2, right? Our different models, if you look at the intersection over union or the dice score, the most complex model, our UNET, actually doesn't do the best by any means, right? It looks like it's on the worst end of the performance. So this is where they introduce their innovation. This is where they bring the domain knowledge of being a material scientist to this segmentation challenge. They're going to introduce this modified Murakami value. Essentially this root A modified value, what that's accounting for is the distance of that defect from the surface, right? So it's an actual distance here. When you look at the different samples from this benchmark data set, some of these are closer to the surface than others. Take a look at this RBF 105 sample. It's going to be relevant in a moment. It's very, very close to the surface, whereas others are a little bit further away from the surface. Accounting for that allows them to calculate which defect is the most critical or damaging to the component. In other words, it's not just about the size of the flaw, because their argument is that the stress is not actually uniform throughout the part. It actually is higher bending stress near the surface. And with this approach, check it out. On their 4 different samples, the actual initiation site is shown as stars, and the 4 different models in the first 3 of these are able to capture that initiation site accurately. But in this last sample, the only one that was able to capture it correctly was the UNet. So why is it that our UNet, which was poor performing in terms of die score, is doing so much better here? Well, this figure kind of shows it. In this figure, you're showing the difference in this modified Murakami value from the UNet, comparing it with the different models. And you see that in this case, actually, it's systematic. All these models are systematically under predicting the size of that flaw relative to the UNet. So it's actually doing a much better job of capturing the true size of it, even though it's close to the surface. So I think this is a really slick paper. There's some cool takeaways here. First off is that if you just had a data scientist tackle this problem, they would have only gotten so far. But if you pair that data science technique of segmentation with the domain science from materials, you're going to do better. And secondly is that the metrics that you might have been relying on, like die score or IOU, don't tell the full story. And actually pairing that with the domain knowledge allows us to get a better overall performance. I hope you'll take a look at it. This is a cool paper. You can read it in the latest issue of IMMI.